A quantum heat engine just worked near absolute zero. Imagine a heat engine so small that it operates not with boiling water or burning fuel, but with individual quantum components cooled to temperatures just above absolute zero. Now imagine that this tiny machine could eventually help solve one of the biggest engineering problems facing future quantum computers: the enormous number of cables required to control and read their qubits. Scientists at Aalto University have now demonstrated what they describe as the first cyclic quantum heat engine built inside a superconducting circuit, a microscopic device capable of converting heat at the quantum scale into measurable, useful work. While the achievement is more than a fascinating demonstration of quantum thermodynamics. It could point toward a future in which some of the hardware inside massive quantum computers becomes autonomous, reducing complexity, cost, and potentially unwanted noise. To understand why this matters, we first need to understand what a heat engine actually does. A conventional heat engine takes energy in the form of heat and converts part of that energy into useful work. The basic principle has powered technologies from steam engines to modern car engines and power plants. But when engineers shrink a system down to the quantum scale, familiar ideas about heat and energy become much stranger. Quantum particles can tunnel through barriers, exist in superpositions, and display other behaviors that have no direct equivalent in everyday machines. Researchers therefore want to know whether the fundamental laws of thermodynamics still work in the same way when the engine itself is made from quantum components. The Aalto University experiment provides an important piece of that answer by demonstrating a repeating thermodynamic cycle inside a superconducting circuit operating under extremely cold conditions. At the center of the new device is a component called a transmon qubit, one of the basic building blocks used in superconducting quantum computers. The researchers combined this qubit with a resonator and something called a quantum circuit refrigerator dot. The refrigerator is particularly important because it gives scientists unusually precise control over heat at the quantum level. Instead of relying on a massive conventional hot reservoir and cold reservoir, the system can be carefully controlled so that the same quantum refrigerator can effectively heat and cool the qubit at different moments. By sending precisely timed control pulses through the circuit, the researchers drove the system through an Otto cycle, the same general thermodynamic cycle used in some conventional engines. The difference is that instead of pistons, fuel, and combustion, this microscopic engine uses superconducting quantum circuitry and carefully controlled quantum states. The experiment was performed inside a cryostat at temperatures extremely close to absolute zero. Under these conditions, quantum effects become much easier to control, while ordinary thermal energy is dramatically reduced. The researchers connected the transmon qubit to the quantum circuit refrigerator and monitored the state of the qubit throughout the cycle. During the process, heat flowed through the quantum system and was converted into measurable positive work. This is significant because previous theoretical studies had proposed quantum heat engines, but actually demonstrating a cyclic superconducting heat engine of this type required researchers to control the entire process repeatedly and show that the machine could produce useful work rather than simply responding to random thermal fluctuations. The most interesting part of the experiment may be what this tiny engine could eventually do inside a quantum computer. Today, superconducting quantum computers require extremely sophisticated control systems. Qubits operate at temperatures close to absolute zero, while much of the electronics controlling them sits at much warmer temperatures. Signals therefore have to travel through complicated chains of microwave cables and other components between the outside world and the ultracold quantum processor. As quantum computers become larger, this creates a serious engineering problem. A system with a small number of qubits can tolerate a complex network of connections, but a future machine containing hundreds of thousands of physical qubits could require an enormous number of cables. Those cables are expensive, consume space, and can introduce unwanted noise into an environment where quantum information is extremely fragile. The researchers envision autonomous quantum heat engines as one possible way to reduce this problem. Instead of sending every microwave control or readout signal through a long cable from room temperature into the cryogenic environment, some operations could potentially be performed directly within the quantum processor. A tiny engine integrated into the superconducting circuitry could use locally available energy and heat flows to perform useful tasks, potentially reducing the number of external connections required. According to the researchers, this could become particularly important for future large-scale quantum computers. Finland's quantum technology strategy, for example, envisions a quantum computer containing around 1,000 logical qubits by 2035. Because error correction requires many physical qubits to create each logical qubit, the actual hardware could eventually involve hundreds of thousands of physical qubits. The researchers argue that building such systems with today's cable-heavy architecture could require millions of microwave connections, each carrying significant cost and adding complexity and noise. The new quantum heat engine is therefore not simply a miniature version of a traditional machine. It represents a different way of thinking about how future quantum hardware could operate. Instead of relying entirely on external equipment to control every part of a quantum processor, researchers are exploring whether some components can effectively power or control themselves using the physics of the quantum system. The Aalto experiment demonstrates the basic principle, but it is important to emphasize that this technology is still at an early stage. The current device does not mean that massive quantum computers can immediately eliminate their cables, and the researchers still need to improve the design and develop systems that can operate autonomously in practical quantum computing environments. Nevertheless, the experiment connects two worlds that once seemed very different: thermodynamics, the science of heat and energy, and quantum mechanics, the physics governing the smallest scales of nature. By demonstrating a cyclic heat engine inside a superconducting circuit, scientists have shown that quantum systems can be engineered to perform familiar thermodynamic functions in an entirely new way. And if future versions can be integrated directly into quantum processors, these microscopic engines could become part of the infrastructure that makes truly massive quantum computers possible. The machine itself may be tiny, but its potential impact could be enormous. Instead of simply building bigger quantum computers, the next breakthrough may come from teaching the quantum hardware to do more of the work itself.